Good morning, everyone. So my name's Jonathan, and I'm joined today with my teammate Puja. And today we'd like to introduce you to the P2 Tower, a workflow for re-neighboring the vertical city. And before we start, I'd like to thank Alif, Malad, Mike, and all of our tutors, as well as our MSc teammate, Pan, for all their support and help throughout the thesis. So within architecture, there exists this paradox, which lies in the fact that over time, people's sociability changes, yet the buildings they occupy do not change to accommodate their new needs. And densification around the world has increased this problem because architects and urban planners responded to the immediate challenge instead of looking for a lasting solution. And this problem is only projected to worsen in the future, particularly in Hong Kong, where rapid densification focused solely on private spaces, leading to the proliferation of the Hong Kong tower block. Yet, the rigidity of the tower block prevents spaces from meeting people's sociability needs, and this has detrimentally impacted the quality of life for people. Such a discontinuity becomes evident when viewed through the lens of unauthorized built works. These are secondary structures built onto existing buildings by its occupants to provide lacking spatial and programmatic needs. And this has culminated in the construction of entire rooftop villages. Numerous architects and urban designers have attempted to tackle these challenges throughout history, including Archigram and Metablis, but most of these proposals sought immutable solutions to immediate challenges. Therefore, our thesis calls for the idea of an evolving architecture by developing a computational workflow which generated a new housing typology and urban network system that met the density needs of cities while also facilitating continuous spatial changes to match the needs of people over time. When we talk about the terms public and private in an architectural setting, we're specifically looking at them in terms of sociability. Based upon this notion and existing research, we developed a system which enables us to quantify the sociability of a space, particularly as it changes over time. And this enables us to adapt a space to meet people's changing needs. Our system operates based on a series of measurable parameters that exist within an architect's scope. And here you can see a few examples of how those parameters are measured. And the focus of these parameters are split between an MSc and MArch phase. During the MSc phase, it began with the design of the fixed systems of the tower morphology, and the structural system. From there, design examines the adaptability of the tower at 3 different scales of space and time: the public-private segmentation of the tower over the course of decades, the program topology over the span of multiple years, and the spatial organization over the timescale of a few months. These adaptable systems were enabled by our fabrication system of robotic 3D printing and traditional bamboo weaving techniques. So during the MArch phase, we revisited those sociability parameters to develop a micro-urban network that connected both the tower to its local context, as well as these local contexts to create an overall urban network across the entire city. And this is that workflow that we developed during the MSc phase. So during the MArch phase, we expanded this workflow into the urban context. However, in order to do that, it was first necessary to revisit the tower's form, structure, and space distribution to enable that connection to the urban environment. Looking at the tower's spatial distribution, the previous model solely considered public and private spaces in isolation. The remaining zones were merely leftover spaces for future growth. So in the MArch phase, we introduced these leftover spaces as both their own elements within the tower, serving as both the tower's space for growth and a transition space to the urban context. In the MSc phase, we also developed a structural system based on the vertical node distribution principles of a bamboo stem. However, the strategy proved to be flawed because we didn't consider bamboo's continuous membrane, which is largely responsible for its structural properties. So in the MArch phase, we integrated the key mechanisms of that membrane, such as its multi-layered shell, directional fiber alignment, and varied thickness. The workflow for the MSc phase considered the development of these systems linearly. However, since these systems are inherently connected, it was necessary to reevaluate their position in the workflow as concurrent systems. And to facilitate that, we used a co-evolutionary algorithm which expands on a traditional multi-objective optimization process by introducing 2 interconnected populations which evolve in parallel. Throughout this process, the 2 systems share data to inform their optimizations, which in turn creates a stronger collective. We developed a plugin for Grasshopper to enable this parallel evolution, which cycled between optimizing each population independently and optimizing the shared parameters between the 2 collectively. Initial experiments showcased the potential for a coevolutionary algorithm to be a powerful tool for optimizing complex systems. While the results did not show an ideal optimization, it was observed that the two independent populations began to converge alongside their shared fitness criteria. And when we began to compare this methodology to traditional multi-objective optimizations, the results show how a coevolutionary algorithm addresses common pitfalls of traditional evolutionary algorithms by dissecting a complex problem into manageable parts. So after initial explorations with the coevolutionary algorithm, we employed it on the structure and spatial distribution of the entire tower with the goal of achieving an adaptable structure system and a context-aware program distribution. And the results show a much more holistic tower where these discrete parts work together as one entire system. And comparing the structural system to a typical crawl-space structure, we can see how the CoEA facilitated one which is more continuous and uses less material. And we can also see how that structure and an internal organization operate within the tower and more closely align with the logic of our adaptable workflow.
Once the tower was redesigned with the context in mind, we moved outward during the MArch phase to consider how the tower itself connects to the urban context through a series of urban pedestrian networks. On the micro-urban scale, these networks served as bridges between the tower and its surroundings, and on the larger urban scale, these pathways were used as program spaces and multimodal transportation networks. At the micro-urban scale, the pedestrian pathways stem from that newly developed transition space of the tower. The heights of these selected nodes are mediated by the heights of the local context. From there, offsets are created from the surrounding context at the height of each node. Intersections from these paths are then created and weighted based on the sociability of surrounding buildings. The pedestrian pathways are then created by finding the closest points with the most similar sociability weightings in the urban context. But since the selection of nodes and pathways did include a level of randomness, a multi-objective optimization was necessary to develop appropriate results. Through this, we aim to achieve a high closest centrality, high path efficiency, and minimum displacement. The results showcase a series of pedestrian networks which bridge the tower to its local context by considering that social influence of the surrounding site. And we can see how those pathways connect to its urban context in the tower. However, while these pathways are optimized towards our goals, it was difficult to understand how the residents would potentially use these pathways. With that in mind, it was necessary to integrate a pedestrian simulation to further analyze these networks. However, existing pedestrian simulations lacked key mechanisms which were necessary for our project goals. They lacked vertical movement capabilities, were limited to physics-based simulations rather than network-based ones, and most importantly, they lacked any consideration for social interaction. With those key flaws in mind, we decided to create our own pedestrian simulation plugin, which introduces vertical travel paths at an urban scale and crafts those social interaction behaviors for each pedestrian. And here you can see a simple example of that plugin, which uses those social factors as drivers for the algorithm's behavior. This type of simulation unlocks new potentials for not only understanding how people use these pathways, but also how these pathways can become drivers for community gathering and socialization. We can see here how the pedestrian simulation runs, how people interact, and finally how you can analyze those results to get quantifiable data. We ran the pedestrian simulation on 3 highly optimized networks from our multi-objective optimization, and the results clearly show which pathways are more effective for travel and social needs, and which ones remain largely unused. Comparing our best performing network against existing ones, we can see how our pathways improve upon the existing site conditions to create shorter travel paths and increase social interaction. And as a result, these studies showcase the impact of those pedestrian simulations, particularly how they use social interaction as a driver of design. Now let's move on to the urban network. We just saw how the P2 tower connects with its local surroundings at the micro-urban scale. However, we should also consider the relationship between multiple disjointed networks and how they connect with each other to form a holistic macro-urban system. To do this, we mapped out each network on a non-metric temporal graph, where the nodes represent P2 towers at various stages of time, and the edges represent the paths that connect them. This approach allowed us to conceptually connect the developed tower networks and understand the relationships within the entire urban system. To create a robust network that performed to the same standard even as it changed over time, we performed a multi-objective optimization on the temporal graph. 3 temporal shifts were applied to the initial graph over the time span of days, months, and years. The initial state was then evaluated independently, while the state of the graph after each temporal shift was evaluated collectively for the same fitness criteria. This method enabled the creation of a robust network, which inherently include redundancies and flexibility. The results of the optimization highlight how this experiment developed a strong workflow to create performative networks that functioned well both initially and after temporal shifts. However, we cannot simply superimpose these graphs on complex urban environments in Hong Kong. Therefore, we employed a weighted shortest path algorithm to translate these connections into context-specific architectural corridors. By analyzing Hong Kong's open source data for the city, we used 5 weightings: closeness centrality, daylighting, hours, distance, visibility, and elevation to weight the algorithm and create context-oriented connections between multiple towers. Additionally, we introduced biases for these weightings to align the developed paths with design-specific goals. Here you can see the effect of those biases on a path connecting 2 tower sites. In doing so, we can maintain the connectivity of the temporal graph while still ensuring context-specific natures of those urban systems. Along these paths, the architectural design of the pedestrian corridors emerged from a modular component. The size and morphology of the component enabled various aggregations which responded to the context and design-specific goals and enabled future adaptation. The angle of the component also enabled high structural performance while minimizing the impact on the ground plane. 3 typologies of these paths were developed in response to specific social, programmatic, and infrastructural requirements. But in order to develop these paths, we conducted a multi-objective optimization on the aggregation of the component, which aims to tailor their performances for those 3 typologies: light rail use, pedestrian use, and mixed transportation use. And the results of the optimization provide a wide range of design options. These options were then used to create a catalog of context-specific aggregations. By combining aggregations of varying performances along with the previously identified paths, these pedestrian corridors can adapt and respond to social and environmental changes over time. To further understand the impacts of these paths, the previously developed pedestrian simulation plugin was expanded upon to understand the impacts of the corridor in their local context. By weighting the mesh based on the sociability of existing buildings and the surrounding program, this pedestrian simulation analyzes how people would move and interact throughout the space. The information gained from the simulation can then help generate locations for future program and showcase potential adaptations for the existing ones. In doing so, the simulation not only analyzes how pedestrians may use these paths, but also enables a generative design system that allows these paths to change over time. To fabricate the programs on top of these pedestrian corridors, we implemented a material fabrication system which was developed during the MSc phase. This system uses concrete and 3D printed woven bamboo. Bamboo is a widely abundant material across the globe and grows very quickly. And when paired with 3D concrete printing, it can reduce material wastage and create unique forms. During the MSc phase, we thoroughly researched this material system, gaining control over its parameters of the bamboo weaving, the capabilities of 3D printing on top of woven forms, and the translation of these metrics into a digital workflow. These studies concluded with a large-scale mock-up to test the development of the fabrication system, which you can see over there.
Now let's see how that entire workflow comes together in a site-specific case study. Analyzing the existing buildings and road networks of Hong Kong, we mapped the population density of the districts over a span of 5 years. And we identified the connected districts of highest density for further consideration, selecting one of these areas for the intervention of our case study due to its diversity. Looking closely at one site, the design for the P2 tower was driven by 4 interwoven narratives, which follow the changing needs of a family unit as they grow and shrink over time. Through these narratives and the case study, we will highlight the ability for the P2 tower to meet the density needs of Hong Kong, while also facilitating continuous spatial changes. The morphology of the tower responds to specific climate conditions, such as daylighting, wind, as well as context-specific density requirements. And the use of the bilayered principles of bamboo nodes enabled the structural system of the tower to balance its embodied carbon and structural performance. Internally, the distribution of public, private, and transitional spaces compete with one another to maximize their individual performance criteria, as well as their relationships with the context. And here we can see how that translates into a cohesive blend of varied program vertically. Looking closer at the design of the component, the fabrication system enables this interwoven nature of private and public spaces throughout the tower. So when we look at a cross-section through this tower, you can see how these new spatial relationships reimagine the way in which people live. And extending beyond the tower, the pedestrian pathway serves as a bridge between the tower and its local context, allowing the P2 tower to enhance the sociability of its local context. Connecting multiple towers together to create an urban network, the multimodal corridors respond to specific social, programmatic, and infrastructural requirements over time by understanding the socio-spatial movements of people in their local context and utilizing these understandings as drivers for generating future spatial and programmatic layouts. And here, or in the model beside me, you can see how all these just discrete elements of our computational workflow come together to create a cohesive urban system that facilitates continuous spatial changes. And when we extend beyond the immediate site of our case study, you can see how the overall urban network, which connects a large swath of Hong Kong, and how the adaptable nature of our construction method enables a dynamic urban environment. Now let's take a closer look at the adaptability of our system. So on this timescale of months, you can see how the material fabrication allows the spaces to adapt internally. On the timescale of years, you can see how the spatial organization enables spaces to expand and shrink as a family unit grows over time. And on the timescale of decades, you can see how the pedestrian pathways and multimodal corridors respond to large-scale urban shifts through the modularity of the structural system. So as we scroll along a street section of Hong Kong, you see how the urban system we developed through our computational workflow both influences the sociability of the urban environment, as well as dynamically responds to changes in urbanity over a multitude of different scales. Thus, the P2 tower calls for the idea of an evolving architecture, one where people determine both the past, the present, as well as the future of the spaces they inhabit. While we've applied this workflow to Hong Kong as a case study, the roots of the system could be applied to other densities around the globe. Of course, the details of the system may change with the local context, but the overall framework can be used to address this dual issue of densification and ever-changing sociability. And so the P2 tower follows in the lineage of the original spirit of Archigram Metabolist, but also treads its own path by proposing a systems-thinking approach to the design process. With the expansion of the P2 tower, we hope to work towards a built environment that always transforms with us. Thank you.
Thank you, guys. Congratulations for your presentation. It's really beautifully presented and clearly quite a lot of work in there, connecting few very sort of important challenges in terms of density, which is something that is quite close to me in a sense. I do want to take this exercise into kind of parts. I mean, I think that the tower, I do like your approach. I sort of would like to understand a little bit more about vertical transportation, which is the main challenge of kind of reconfiguration in a tower block. So are you sort of proposing to eliminate the core centrally and redistributing the structure outwards?
Yeah, so the idea with the vertical circulation, the tower, is to remove that traditional idea of a central core for transportation. That's why we use an exoskeleton to transfer all the loads to the outside of the tower, and then that third transitional space that we discussed previously sort of weaves vertically throughout the tower, and that's where that main source of circulation would be.
And I do understand what you're trying to do in terms of like assessing the changes of the spaces throughout the different scenarios of a family growing into an old couple, but I don't quite then understand how that relationship becomes evident when you're trying to plot the connection from the tower to the rest of the city, because you decided and you picked up specific parameters such as daylight, so I can't remember them all now. It went very quick, but I was sort of more curious to understand how this neuralgic activities around the city would influence that. So I think the second part for me, when you're trying to connect and distribute the network, it feels a bit like that you might have to do a little bit more work in justifying that. The other problem I have with that is just a bit of and it's a bit technical, I think, it's the height that you picked up to distribute that network, because it looks really high and you might catch quite a lot of wind speeds, and it might become an uncomfortable space, therefore not quite used. So I think these are my main two comments, I think.
Yeah, I was looking for that core that I could never see in your plans. So you see there is no core, right? And the structure is on the outside. But I also don't see that vertical connections happening. I don't see it in that drawing, for example. How the hell am I going to go to level 20? Right, I'm going to walk up. So that is you kind of, it's kind of interesting because you showed in your analysis of that tower, you only showed kind of sections, and it almost was like you kind of took that section as like an urban plan, I think, analysis. So a lot of other groups I saw doing, urban analysis and on a plan. You guys did it almost as a section, but it doesn't work like that, right? Because you do have that, going vertical is much harder than going horizontally. So I'm kind of missing that, and I really think that's a really point that you really need to tackle, because otherwise it doesn't quite work. And I've got the same comments here, why do I want to go from one tower to the other tower? What is there for me to go to, right? That is actually the attractors in your analysis is really important. It's kind of funny because you kind of did the whole thing quite two-dimensional, but then you did write your own little plugin that did three-dimensional movement, which also was like kind of bizarre because you had that, but then you didn't actually use that to start designing this tower itself. So I was kind of confused by that, right? That you seem to have written the tool, but then never used it. There's no kind of proof of that in this drawing, which is a great drawing, by the way. So anyway, I'm just kind of saying the same comments here. So I want to ask a question. What wasn't clear for me was how the bamboo and the 3D printing are working together. If you could kind of explain that a little bit more, how that kind of combination works, that wasn't clear in the presentation.
Mm-hmm. Yes, so the bamboo would act as formwork. You weave that first using the techniques we described, and then you would 3D print on top of the bamboo formwork to create that solid layer on the outside. So we tested this with weaving and clay printing, since we didn't have concrete here, and then we casted this one to show the concrete adhesion within the bamboo cells.
Yeah, but to understand it on a larger scale, how that works as well. I can see there's a detail,
yes.
But how that really for tower construction would really work. So I think there's a lot to kind of research there. I feel. I just another comment. I really like your presentation, how you kind of animated it quite well, and it flowed really nicely. I think that was actually really good. So well done on that. But yeah, that vertical connections, we got to sort that out.
To answer that one point about why we didn't use the pedestrian simulation on the tower was mainly because we didn't have the pedestrian simulation when we developed the tower during the MSC phase, and we didn't have time to revisit. But so they're sort of developed separately when, you're right, they should have been used together.
Okay.
Thank you, guys. It was very proficient presentation and very ambitious also. I think, well, first, congratulations, because the work, it's difficult to approach as a critique because there is a lot of thought in it. To me, maybe what I keep thinking is like, what is the bottom line of the proposal when we see this model, no? And I feel like there are like two main areas. One is this superstructure. I wonder if it could be more refined in terms of how it is soft in the bamboo phase and then it becomes rigidified. Like, how to go from the more rigid structure, maybe of thinner elements? What is the kind of typological challenge that you are kind of surpassing by trying to work with a softer material and going to the rigid structure? And then maybe you could challenge height. I feel that there is a criticality there that's still not built up. Like, you can do things, and you say how you can do them, but maybe like the reasons why you would do them and what it involves at an urban scale, which I'm sure you thought of it, but you haven't stopped. Like, the presentation was very kind of high speed all the time, and maybe you would benefit from stopping and saying, and with this, we think that we are challenging this problem and this other problem. So that would have been beneficial. And then the other realm is the street network that all of a sudden you kind of explode, and you say there is a need for a rooftop approximation. And you say why at the very beginning, and it's pretty actually, it's a huge problem. So you say there are slums in the rooftops. Okay, what do we do with that? I'm not sure you are being, let's say, careful about that afterwards. You just build the possibility of the rooftop. So if I sustain that for a moment and I say, okay, I don't look at that problem anymore, and I look at your system, then is this network that you're speaking of something that works with the street system? So then it doesn't overlap with it. And then how does it work with the rooftops? So instead of focusing so much on how to incorporate more sociability, I would say, how are you knitting together the three-dimensionality and raising up a sort of, like tighter density system? But you know where I'm getting? Like, in both scales, I'm getting to the why would we do it, how, and then I know you can do it, and I know you can actually implement a kind of optimization process, but it would have been great to hear you stop for a moment and then make us reflect on those two, at least at those two scales. But really good job, and thank you.
Thank you.
On those, sorry, just one more thing. What you mentioned on the connections, right? You kind of copy the roads, don't you, in that model?
Yeah, it follows the road. That's kind of strange.
I mean, I think, thank you for the presentation. I think I echo the comments. Presentation-wise, I really like it. I think it flowed really nice, very smoothly, really nice presented and explained. For me, I think it's sort of, I also miss the vertical connection a little bit, so that I'm not going to repeat the same comments. I admire the fact that you created your own pedestrian simulation in a way. So in order to try to resolve or understand certain issues. So I don't know if you know, but there's a whole open access pedestrian network of Hong Kong, 3-dimensional. Yes. That would be nice to actually also understand the existing context and how that connects to your, towers and so on. I'm also happy that you guys implemented, and some of you at basic level, the whole area of network theory. But having said that, I think that, one of the things that I see a little bit lacking is the urban story behind the tower and the location of those things. It was mentioned, that you actually identified the slums, you identified the problem, and yet you didn't tackle necessarily the problem with your solution. Mm-hmm. So that's one thing. And the other one, you were choosing different locations of where to implement this network of towers. And my first question is, why those locations? Are there empty lots or are not empty lots, etc.? Because every single one of these has their own unique context around it. So I think that part of the context is missing for me. And in matters of, if you want to build a tower, however high or tall, Hong Kong is a maze of network, not only 2-dimensional, but 3-dimensional. So if I think about the, and the proximity concept of the 15-minute city, right? This could be well endowed, a program of a 15-minute city vertically, or maybe less, right? 10-minute, whatever. And I was wondering about the program of that tower that could actually happen inside of that in the same way that we see throughout the city. So, for me, program was lacking a little bit. The connectivity or the connection and the link vertically, that, it's a whole purpose of the tower in Hong Kong. And again, the understanding of that context that speaks of the sociability. I would have loved probably to, go back to your beginning of your question and the problematic to say, if the slums are like this is how can be improved. This is how you can, rather than to make a new tower, is how do you do it in the existing ones? How do you tackle the existing spaces? I think, it's also a matter of, yes, constructability, connectivity, mass transit, pedestrian flows, but I think it's not forgetting to tackle the real problem that you're looking at, and don't walk away from it and then, well, this is the proposal, right? Is how to integrate those two things. Beyond that, I think the presentation was lovely, super nice graphics, very nice, very nice shown. But yeah, thank you for that.
Thank you.